So I can't do my usual jump-in intro today because I've got the circuit in my hands. But what's up? Today I want to run you through what my digital design project looks like. I finished this about a week ago. I'm actually just busy working on the report for it. There's a spider web in there right now. But this is what I had to do for digital design this semester. Obviously the practical that we had to do was adapted for online since we all had to do it remotely. And we actually did this in teams, but this is my portion of the circuit. And my two other guys in my group did the other two parts. So we were supposed to do like a robot car, self-driving robot car kind of build with a whole lot of other stuff built in it, like a power supply, motor driver circuit, sound detection circuit for obstacles on the track, and if it detected a certain frequency of sound, it had to stop the car, a screen, OLED screen, some kind of display to let the user know what's happening with all of the different specs of the car at the current moment. That's just state indicators. That's an ESP32 microprocessor. So yeah, let me plug this into my computer and show you how it works. It's not the most visually impressive, but I learned a lot of skills and a lot of technical know-how doing this practical, and I'm happy with it. I'm happy with the way it turned out. So just so you know, that there is the ESP32 microprocessor. That's just 4 LEDs to show the specific state that the system is in. That's my OLED screen, 128 times by 32 OLED screen. That's my microphone. That's I think it's an LM326 op amp and capacitors in that just for an amplification circuit. And that is my hardware. So let me jump straight in and show you what I have in my code. C++ Arduino code for the ESP32, and what actually the prac guide said that we had to do. So as I said, the practical was split into 3 parts. The state control system, come on, how do I zoom on this ish? Press the right button on the keyboard. The state control subsystem, the motor driver and power supply system, and the sensor subsystem. So my 2 groupmates, Avoidance and P-Ware, did the sensor and motor driver system. I had the state control system, which I had to have an activation prompt, a color selection, a display, collision avoidance, steering control, and communication and control. So the activation prompt and color selection were both capacitive touch buttons. Well, I decided to use them as capacitive touch buttons since the ESP32's got capacitive touch buttons. So that's literally what this wire here is. When you press the button, it registers a different value to when the button is not pressed, and using that constant difference in values, you can determine whether the button has been pressed or not. And I use that to change the states of the system. Then the display is this little OLED screen here, which I'm intersperse some close-up footage of this so you can see. But that's this OLED screen here, which I coded with, I think it was the U8G2lib library, which is really cool and useful, and you can do a lot of stuff with just a small, a 128 times by 32 OLED screen. And it's actually really cool to actually work with an OLED screen and see how maybe big devices like your cell phone work on exactly the same principle. You know, it's just a huge grid matrix that you can draw on, and obviously, okay, a lot more complicated, but this grid matrix is the same as this little grid matrix here, and it was cool to play with, and even if you just use a library, it was cool to master. And then the collision avoidance was basically the sound detection circuit here. So because this practical was supposed to happen on campus and in person, you know, you were supposed to move along the line and avoid obstacles, that kind of thing. But because this was happening online, they decided that when a specific frequency was played, your car had to come to a stop, issue some commands, and then reverse backwards for a bit. So I had the sound detection side. So this is just a microphone here, along with an amplifier. I think it's an LM326 or that model of op amp there, with some capacitors in that. It's just an op amp, an amplifier circuit, to take the sound that's generated by the microphone and then amplify it a bit and feed it to the ESP32 so that it can recognize, then using the, I think it was the Arduino FFT library, recognize which frequency in particular was being broadcast by the hub, or being broadcast at least in the vicinity of the microphone. And then when the specific frequency was detected, it would trigger some actions. So it would move from the race state to the SOS state, that kind of thing. And that's all the hardware actually. These LEDs here are just the state indicators. Let me talk you through the software now. So there was 4 different states that we had to implement: an idle state, a calibration state, a race state, and an SOS state. And in each particular state, something in particular had to happen. So over here in my Arduino code, I'll show you, this is just my startup, including libraries, variables, defining values and whatever. But then in my main code, I had a state, basically a state switch block. So in Arduino, you have a loop that runs continuously while the Arduino is on, or ESP32, same thing, runs on the Arduino framework. Well, the Arduino framework is running on it, but I'm getting sidetracked here. So the state switch block here basically just checks what the current state is. If it's idle, it sets the specific light to show that it's in the idle state, and then it runs the idle state method. It does the same for the calibration state method, the race state method, and the SOS state method. And then each of those is just a method that runs continuously while that state is active, and then does a number of certain things. So when you're in the race state, it receives a whole lot of input from the hub, which is a piece of software that the one assistant lecturer, Dwayne, the guy who demoed me, actually wrote. Incredible piece of software that he actually wrote. It's over here in the corner. That we have to connect our system to, and then it feeds our system different information based on which system and which state we're in at the moment. So basically, when you're in the race state, you receive a lot of input about the specific motor speed that's currently happening, the battery level of the motor, the battery level of the power supply, the current speed the motor is spinning at, the current race state, and then you have to feed that information to your OLED screen for user display. And then in our demo, we actually had to show that, and we had to show that our system was working. And so that's what this code here is just doing. It's just checking what the deviation of the sensor is to the left or right of the track, what the motor speed is, and then using serial to either print that out to the hub or using it to print it out to the screen. So you're working with binary values in that. The serial communication took a long time to get right, just because it was finicky to work with the hub. And yeah, you can actually use whatever subsystem you want, whatever components you wanted to build this. If you wanted to do it in in assembly with PIC 18F45K22, hey, I'm still impressed that I remember that name. If you wanted to do it with that, you could, but obviously that's a lot of work, so most people just decided to do it with an Arduino. So that was the race state, basically. What happened in the race state is it's constantly receiving input from the motor and sensor subsystem, and then deciding whether to move the car, to send instructions to move the car to the left or right by applying different voltages to the motor subsystem. And in the idle state as well, it was just waiting to receive the capacitive touch input and deciding which line of the track which color line on the track you're going to follow, red, green, blue, extreme, yada yada yada. And then in the calibration state also there was some stuff happening with the sensor and the motor. We had to wait for specific calibration, you had to receive input, and you had to write it to the screen. But yeah, I mean that's basically all of the code, and then there's just a few sub methods here like writing to the screen. This is using the UG2 something library. What's it? U8G2 library to write to the OLED screen just on specific places on the matrix. That is the LED screen, and what you want it to say, what emoticons you want to have there, even the little battery level icon. I know it doesn't look like a super impressive project, but it took a long time to get these finicky things working. I actually had to solder this ESP32 to the header pins, because I battled for ages and ages and ages as to why my screen was sometimes working and sometimes not working. And then my friends told me it's probably because I don't have solid connections. And so then I learned how to solder with the help of YouTube videos. My sister helped to film the process, and yeah, I spent the morning soldering the header pins to my ESP32, and then it worked like a charm perfectly afterwards. And so yeah, listen to your smart friends, guys, it really helps. So yeah, in addition to all the stuff I learned how to use the ESP32, the OLED screen, more about operational amplifiers, I also learned how to solder properly in this prac, which was really cool. And you know, sitting at home in the middle of the pandemic, learning new skills like that, it actually made the project feel worthwhile. And so yeah, that's all of the methods here. The code is not super impressive, it's just Arduino C++ code. But more getting it to work with this hub subsystem here was what took the most time, and it was quite finicky. So you see here we have to connect to a specific COM port, we have to put in our specific group number, and then connect. And then I'll probably speed this up because you don't want to watch this in slow motion, but then we had to run a specific qualification test procedure, and we had to pass that qualification test procedure to get the marks for that part of the practical. And so this is I'm not sure which qualification test procedure this is. This is one of the first ones. I don't have it open, but anyway, something had to happen in here, and then so this qualification test procedure started in the idle state, and then we moved to the calibration state where the screen came on, it received some input, then we moved over to the race state, and it started receiving input there. And then I'll show you the sound detection qualification test procedure, because that's actually interesting, and you can hear the tones that it makes, and that our circuit has to listen for. And so you hear there were 3 different tones of different frequencies, and the last one was the correct one for my group. It was 1250 Hertz, and only upon hearing that specific frequency did my system transition to the SOS state. So yeah, that's basically the system. I know it's not super impressive. It would have been a lot cooler if we were on campus and we actually, because usually this module you get to design your own system and build it, and you get to kind of do whatever. But because we were all at home, they had to kind of standardize it because not everyone has access to laboratory conditions or components or that sort of thing. And so it wasn't the most impressive, but I still learned a lot. I learned OLED screens, I learned sound detection, I learned ESP32, I learned soldering, I learned more C++, I learned more coding practices, I learned more serial communication. Yeah, all of the stuff that you learn over time and just by continuously working on engineering projects, it's getting better and better, and I feel really good about this prac. I haven't got my mark back for it yet. If by the time I post this video I know my mark, I'll chuck it up there. But I'm also busy working on a report for that. The report for this. So if I'm finished the report by the time I post this video, I'll put the report over there and you can have a look at it and see what it looked like. I know it's split into a group section and then my individual section where you just have to talk about like the design philosophy for the system, how you went about designing it, like detailed software specs and detailed diagrams and that of how your thought process, how your code works, and how your system is just integrated with the whole rest of the system overall. But yeah, that's basically my system. I'm really happy with it, and I really hope you enjoyed learning about what we did this semester in digital design and computer engineering. Not the most impressive, but hey, COVID has caused us all to do some things differently this year. But yeah, that was one of my big projects this semester. Really glad it's done. Looking forward to doing more interesting stuff next semester when I finally take EAI, that's our artificial intelligence subject, and I think also doing computer engineering architecture. That should be interesting. But yeah, that was one of my practicals for this semester, at least the cool one of the cool ones that you might be interested in seeing. So yeah, thanks for watching this video. Hope you're having a good time, and I'll catch you in the next one. Thanks for watching.